Okay, this is the first of several videos that we'll be going through. It's an introduction to problem solving. So let's get started. I'm going to just give you a very brief introduction, and then we will go through a simple example. Okay. So why are we interested in mathematics? And that's really what we're talking about here. The kinds of problems we'll be dealing with in these videos. Math models allow us to make predictions about our physical world. So when we design something, we can predict what it will do and how it will behave. That's the essence of our use of mathematics for engineers. So you'll learn the fine details in the math classes, but there's some big ideas that we can present for you here that provide context for those math classes. And there's a nice idea that I like this quote from Mr. Einstein. Said, if you can't explain it simply, you don't understand it well enough. Well, we understand this pretty well, and we're going to try to make it, as I said, give you the big ideas behind these mathematics that you'll be learning in your math courses. So let's start with a simple problem. It's a real problem. We have an automobile driving along the road, and it applies its brakes. And we want to, by making a couple of measurements along the way, we want to be able to find its initial velocity, how fast was it traveling when it applied the brakes, and what is its deceleration rate, and what is the time required for it to actually come to a stop. Now, this is somewhat of a canned example, but, it applies very well to all sorts of different vehicles, trains, rockets, airplanes, and so forth. So we made a couple of measurements in the field at time 2.25 seconds after it applied the brake. We measured its velocity. Its instantaneous velocity using a radar gun is 62.8 feet per second. And at time 5.5 seconds from the time it applied the brakes, t equals 0, it was traveling at 26.4 feet per second. So now our job is to figure out all of these other things that I have listed here. So there's some typical steps that you can use in solving all sorts of problems. This is an example of a simple problem, and we're going to actually go through these steps solving this problem. Okay, so the first step is to visualize the problem. That is, draw a sketch. What are the variables at play, right? What's known and what's not known? And kind of what are the questions? So, the first thing to do is, as I said, draw a sketch. So there's this nice, simple little sketch. An individual driving a car along the road, and they're traveling at some velocity. And velocity is a function of time, right? Especially when we know they're decelerating, right? So there's a deceleration going on. So we're given the table of times and velocities at a couple of different points. So that's what we're given. So we need to describe the problem. What kind of a problem is this? Well, we know it's a physics problem, right? It's a physics problem. If you don't recognize it, you will as you go along. And what are we being asked for? Well, it said in the problem we're looking for the initial velocity, and at time 0 when the brake was applied, how fast was the car moving, and what is its acceleration or deceleration rate, and then at what time will the velocity be 0? Okay. And we know the relationship among these variables as the velocity and time variables. But what we're looking for then, the unknowns are initial velocity, time at velocity 0, and the acceleration or deceleration for the given data. Okay, so now I need to plan out a solution. What tools can I use to solve this? You know, what are the equations at play, and what's my strategy for doing so? The unknown and unknown variables in the sketches, if it's a more complicated problem than this one. You know, are there any other principles at play? You know, is there enough information, and so on, right? So we're going to go through these steps right now. So we're given the table of information that I mentioned and showed you. We're looking for these unknowns. Not sure what's going on. Okay. But the tools that we have available to us, the tools that we have available to us, of course, are the physics tool kinematics. You know, velocity equals the initial velocity at time 0, plus or minus the acceleration times time. We know that. And that's a straight line. If we recognize that there's a straight line and we've got some data about the line, actually, we have 2 points on that line that define it. Right? So we can find the equation of the line given 2 points on the line. Okay? And we've already identified the known and unknown variables. You know, and is there enough information to solve it? Well, we know that 2 points define a line, and so we're just looking for the information, the other information about the line. So we've got enough information to solve it. This is the formal process, but you know, often, you know, for depending upon the complexity of the problem, you may not need all of them, right? But it's good to think about them anyway. Okay, so what are the constraints? Well, deceleration is constant. We're assuming that, right? We're assuming that the brakes are applied at a constant pressure. Okay. And the steps needed to solve the problem, first we need to find the slope of the line using the 2 points that were given. And then we can find the intercept, plugging in a known time and velocity from those points, and find the intercept. Okay, so here we are. We're going to implement these steps. Here are the data that we have. And the slope equals the rise over the run. Right, so the rise, the independent variable is the run, so that's time. And the dependent variable is velocity. That's the rise. Okay, so the rise over the run. Rise is the difference in the velocity. It's a decrease, so it's a deceleration, right? The decrease is 36.4, and the run is the time difference, and that's 3.25. So the rise over the run is the slope, or acceleration, or deceleration in this case, and it's equal to 11.2 feet per second squared. Okay, so if we plug that in, so here's the equation, and if we plug in one of the values, we know at 62.8 velocity, the time at which that occurs is 2.25 seconds. So the initial velocity then is 88 feet per second. And again, if we plug in velocity as 0, what time will that occur? We can just solve for t, and that's 7.9 seconds. So that's the solution. Now, and I can look at the, you know, the slope makes sense because it's negative acceleration, right? We're braking, so we're slowing down. And I know from experience the magnitude of this deceleration rate makes sense. It's a third of gravity. If you came out with 200,000 feet per second squared, you'd know there's probably something wrong, right? So, this is a reasonable number. And, how does it look? Well, here's, if we just plot the data, you can see that it's, plot these 2 points and draw a line through them. Well, that's right around 88, isn't it? And then this is right around 7.9. So this is consistent with what we calculated. And that's it. Okay, so let me stop here.